So, hello, namaskar to the all chemistry lovers and doctors and engineers of the near future. मैं विजय कुमार सोनी आपका वेलकम करता हूं रिगार्डिंग टू दिस केमिस्ट्री वाला चैनल एज ए केमिस्ट्री टीचर. In previous video we have discussed about the just CFT in octahedral complexes, tetrahedral complexes, it's just square planar complexes, and now we'll go with the CFT in tetrahedral complexes. So what is the basic thing? So this is the CFT in tetrahedral complexes. If we'll go with the CFT in tetrahedral complexes, then this is, we can say, it is inverse of CFT in octahedral complexes. Means here T2G will be the higher energy orbital and EG will be as a lower energy orbital, and maximum compounds will be as high spin complexes. This is the most important thing. Means maximum complex compound will be as a high spin complexes. If we'll go with the just first of all geometry, then metal atom will be as a positively charged according to CFT. This is the M plus N. Ligands will be directed as follows. These are the four ligands as a L minus and minus, because according to just CFT all the complex are assumed as ionic compound. Now time to discuss about the just splitting of the orbitals. These are the 5 degenerate orbitals, as you can say dxy, dyz, dxz, dx square minus y square and dz square. Here is the splitting of the orbital like this. 2 of orbital will be as a low energy and 3 of will be with the high energy. These are known as, you can say, easy set of orbitals, or you can say E orbitals also, while these are known as T2G, or you can call it T2 orbitals. The energy difference is your del T, where del means again your crystal field splitting energy, and T means for tetrahedral complex. If we'll go with the just energy difference, then this is the 0.4 of del T, and this is the minus 0.6 of del T, and this is the barycenter center. You can say this is the barycenter center. So this was about the just CFT in tetrahedral complexes. Means it's just inverse of the your CFT of the octahedral complexes, and maximum complex compound will be as a high spin complexes. These are your dxy, dyz, dxz, dx square minus y square and your dz square. These 5 d orbitals are known as just your degenerate orbitals. So this is the degenerate orbitals. So this was about the just CFT in tetrahedral complexes. Now I would like to go with the just different deconfigurations of the tetrahedral complexes. What are they? Listen me carefully. It's too important. So this is the different configurations for tetrahedral complexes. What are they? We have discussed just it will be two diagram. One of the for the weak ligand, another will be for the strong ligand. And according to CF10 tetrahedral, here will easy orbital, and here will T2Z orbital, like this, T2Z orbital, and the energy difference is denoted by del T. If we'll go with the, this is for the strong ligand field, and if we'll go with the weak ligand field, then the diagram will be as follows. This is the, you can say, for the T2G orbitals, these are the T2G orbitals, and this is for the easy orbital. From the diagram you can say which of the is for the strong ligand and which of the for weak ligand. Easy orbitals, this is the del T, and this is your for the weak ligand field, means you can say this energy gap is larger for the strong ligand, this is lower for the weak ligand. Now the time to discuss about the filling of electron. So first of all we'll go with the D1 for strong ligand and D1 for the weak ligand. First electron will be over here for the same. So it is your Eg is equals to 1 and T2G is equals to T2G is equals to 0. Here is same, Eg is equals to 1 and T2G is equals to 0, and both exist same property as a paramagnetic nature. So this is the paramagnetic in nature. Now the time to discuss about the D2 configuration. This is the D2, second electron. Now the second electron, so Eg is equals to 2, T2G is equals to just 0, and here same, just D2, Eg is equals to 2 and T2G is equals to just 0, same paramagnetic nature. Now the time to discuss about the D3 configuration for the strong ligand. It will be fourth electron over here, so Eg is equals to 3 and T2G is equals to 0. If we'll go for this, then it will be third electron over here, so Eg is equals to 2 and T2G is equals to 1. You can see here is only 1 unpaired electron while here is the 3 unpaired electron, so its paramagnetic character will be larger than the weak ligand field. So this is the both are paramagnetic, but for the weak ligand it will be larger than the strong ligand. Now the time to discuss about the D4 configuration. This is the Eg, this is the fourth electron, and Eg is equals to 4, T2G is equals to 0. Here is the D4 electron, this is the fourth electron, so Eg is equals to 2 and T2G is equals to also 2. This will be paramagnetic, but this will be your diamagnetic because all the electrons are paired. Now for the D5 configuration, this is the fifth electron and this is the fifth electron. So this is the Eg is equals to your 4, T2G is equals to 1, and it will be your paramagnetic. while for this D5 AG is equals to your, you can say for the D5 this is the AG is equals to 2 and T2G is equals to 3. This will be paramagnetic, but you can see here is 5 unpaired electron while here is 1 unpaired electron. So D5 for the weak ligand field will be stronger than the just your weak ligand, strong ligand, sorry. Now the time to discuss about the D6. So this is the EG is equals to again your 4. This is the T2G is equals to, you can say 2. Here will as follows according to Hund's multiplicity rule. So EG is equals to 4, T2G is equals to 2, and here D6 will be EG is equals to your 3 and T2G is equals to again 3. Both will be as a paramagnetic, but for the D6 strong will be less paramagnetic than the just for the weak ligand, because of here is 1, 2, 3, 4 unpaired electron, is 2 unpaired electron, so paramagnetism is larger. This was about the just a different electronic configuration from D1 to D10. Read the entire matter properly because it's too important, and this is the last CFT for the tetrahedral complexes and the configuration also. So now the time to discuss about D7 to D10 electronic configuration. What is that? Listen me carefully. This is the D7 electronic configuration. This is the D7 electronic configuration. This is your 4, 5, 6 and 7. Here is the same. So T2G is equals to, you can say EG is equals to your 4 and T2G is equals to your 3. Here EG is equals to 4 and T2G is equals to again your 3. Both at the same paramagnetism because both at the same unpaired electron, 3 in each. Now the time to discuss about the D8. EG your 4 and T2G will also 4 like this. This is the 4th electron. Here will also 4th electron. So this is the D8. EG is equals to 4 and T2G is equals to again your 4. This is the paramagnetic. Both are same paramagnetic because here is the 2 unpaired electron and here is also 2 unpaired electron. Now the time to discuss about D9. This is the EG is equals to 4. T2G is equals to your 5. 5th electron will be over here and for here will be. So this is the D9 configuration. EG is equals to 4 and T2G is equals to your 5. This will also paramagnetic, and paramagnetism of both complexes for weak and strong will be same. Now the time to discuss about the D10 configuration. EG is equals to 4 and T2G is equals to 5, 6. This is the 6th electron, all are paired, and 6th electron, all are paired. So D10, EG is equals to 4 and T2G is equals to 6. Both are diamagnetic because all the electrons are just paired. So what we can say that result, you can say D0, D4 when there is strong ligand, and D10. These all are diamagnetic, and rest all will paramagnetic in nature. Paramagnetic nature. So this was about the just different deconfiguration regarding to octahedral complexes and tetrahedral complexes, and you can say CFT in tetrahedral complexes. इसी प्रकार से मुझ में विश्वास जताए रखिए और केमिस्ट्री वाला पे ट्रस्ट कीजिए। आपको हर एक टॉपिक के रिगार्डिंग वीडियो अपलोड की जाएगी और हर एक कंसेप्ट को आपको क्लियर किया जाएगा। धन्यवाद, शुक्रिया।